Okay, so let's get started back up again. Just a reminder, this afternoon we're talking about Python and R specifics on ARCHER2, how we use them, how we can do parallel or run many workers, Python workers programs at the same time. And we're going to start off with Python, then we'll move on to R later. I mean, the first thing to say for both of these is there is no significant difference between Python on ARCHER2 and Python elsewhere, or R on ARCHER2 and R elsewhere. For the majority of things, they're just Python, they're just R. You just use them as usual, with the caveats we've already seen around you need to install things on the work file system, and we need to use things for a batch system, all those kind of issues we've seen. And if you want to get good performance and you're running lots of copies of a program, you might need to tweak how you arrange them on a compute node, as we've seen. But beyond that, the standard languages shouldn't be any different, really. You know, this is just computers, and the interpreters just deal with those computers. So the Python interpreter or the R runtime both just use that as you would expect. Where things do diverge a little bit, or where there are some specialties that you may want to care about, is when we start getting into this idea of running multiple things at once or doing things in parallel. And most of Python and R, you wouldn't worry about those kind of things. You wouldn't focus on those kind of things. But because, as we said earlier this morning, this is a large application, a large compute resource, and it's set up for running lots of jobs at once or running things that need a large amount of compute, you're not really going to be coming to ARCHER2 to do small jobs, things that only need one core for 5 minutes. But that you wouldn't have ended up on ARCHER2. Now, of course, that's not to say people don't use Python and R and ARCHER2 for those kind of things. Maybe a little bit of analysis of data, maybe a little bit of preparing job input or processing job output. That can all be done on R, but that's not really large-scale use of ARCHER2 with Python or with R. When you're getting up to large-scale use, then we have to start looking at how you do things in parallel. And we've already seen this morning, one of the ways we can do things in parallel is run lots of copies of the same job, and then just inside your Python program or your R script, you can read in different files and process them separately. You know, you can run an array job, you can read in from the command line an array ID, as we saw this morning, and then use that to say, okay, I'm working at 100, I read this input file at number 100, and I do lots of work like that. Well, that's perfectly possible. In some ways, it's a slight waste of ARCHER2 because you're not using that nice high-performance network for anything. But it's definitely a valid use of a large-scale system. If I've got 1 million files to process, and that would take me months on a local resource, I could go up to a system like ARCHER2, or some of our tier 2 systems like Cirrus or other ones around the country, where you'd say, okay, I want to take 10 nodes and I want to run 1,000 copies of Python, and each will take 1,000 files, and we'll get through that much quicker, much more quickly. Of course, once you start getting up to then, each file is very big and it takes a long time, then you start getting into the realms where, well, even then, we need to parallelize an individual program, an individual Python program, an individual R program. And that's what we're going to talk about in the next couple of lectures, how we do those kind of things. So we'll look at Python first. There's two kinds of parallelism here that we care about, two main kinds of parallelism. It says a recap here, but you may not know this already, so it may just be telling you. We have this idea of shared memory parallelism, and we also have an idea of distributed memory parallelism. Basically, shared memory parallelism lets you run workers that cooperate together, but only inside a single node. So you can write a program on ARCHER2 that runs up to, say, 128 cores. If you're using a shared memory approach, you can't go beyond that. That may be useful for you, but it's also limiting in the long run. So there is another way of parallelizing things called distributed memory parallelism. And there you can use multiple nodes at once, and you can scale up to the size of a whole ARCHER2 system. Why do we have these two distinctions? Well, it turns out the way computers work, it's pretty easy to write a shared memory parallel program because, and we don't need to go into details here, but individual workers, individual processes, which is a running program, they can create their own workers, which I talked about a little bit before lunch, called threads, and they can create as many of them as they want, as long as they're inside a single operating system, inside a single compute node. And so you can easily parallelize a program with this shared memory approach, and that's what OpenMP is. And we saw earlier in some of the practicals we were using OpenMP threads for the XTHI program, or setting OMP num threads to control that parallelism there. And that's just an easy way of doing parallelism. It doesn't let you go beyond a node, but because you're inside a single operating system with a single program, it's a simpler way of programming and developing the application. If you need to go beyond a single node, when we go to this distributed model, where you have to write in the functionality to explicitly send messages between individual workers in the program, you can't any longer rely on them sharing their own workers inside a single operating system, inside a single computer. So you have to explicitly write in communication patterns, and that tends to be harder, more involved task. And so generally people use a library called MPI to do this, message passing interface, but you have to restructure your program to be able to use that effectively. And so it's a harder thing to do. Now Python is set up to use that first option, that shared memory inside a program, inside a compute node parallelism, relatively straightforwardly. There are a bunch of built-in libraries which let you do this. One is called the threading library, and there you can create workers, give them work to do, and they go off and do their work. So as an example, a bit of code here, where we've imported the threading library. We've defined a function that a thread is going to run, and in this case, a thread is just a worker of the overall program. And then through here, in the main program in our Python program, we create 3 threads. So I'm looping over a range 3, and I add them to a list, and then I start them, and then at the end I collect them together. Okay, so I can create workers in this using this threading library pretty simply. There is, however, a problem in Python, which we call the global interpreter lock, or the GIL, which means that you can create as many workers as you want here, but in standard Python, only one will ever run at any one time. So they don't run in parallel. And that's just because Python lets you update the program whilst it's running, interpretive mode particularly, and so it can't have multiple workers updating the source code at the same time. So that's a challenge for Python. There is an alternative approach, which we call the multiprocessing library, where you can create workers that are not threads, the individual processors, and they can run in parallel. And so this is sort of what we would call distributed computing, not necessarily parallel, but distributed computing, things that can work at the same time. And give me a second. Yeah, so in this multiprocessing library, each process you can think of as having its own Python version, its own process. So in this multiprocessing approach, each process would have its own version of memory with its own data in it, and they work on separately. And if you need to share memory data between them, then you have to use these queues or pipes, where you explicitly send the data down the queue or the pipe. So in this example here, we've got a process which we created, and we create a queue, and then we get and put into that queue to get data to and from each individual process. So we create a main process here called P, and then we have another process which puts at the top here, and one process which gets at the bottom here. So the function f is going to be run on a separate worker, and then the main original process will run, it will get the data from that worker. And you can see in the left-hand side, we're using a put and get model on a queue. And then on the right-hand side, we're using a send and a receive model on a pipe. But they're doing effectively very similar things, where we explicitly are sending our data backwards and forwards. So this is very much like that distributed memory model, where we're explicitly having to write our communications. In Python's case, in this setup, you'll still only be able to use all the workers inside a single node, but at least those workers when working can run in parallel. However, this is not really designed for high performance. This is designed for concurrent or distributed computing rather than parallel computing, because the communication mechanisms it uses for those pipes or queues aren't really designed for high performance, and they don't map down to our fancy networks we have in HPC systems. So there are other things we can do to do parallelism in Python. One is to do implicit parallelism, and that is to use something like NumPy or SciPy, which themselves call lower level libraries in C or Fortran, which themselves are parallelized. So you've got to do large matrix operations, large algebra, linear algebra operations, and some of the scientific library operations. You can just get your parallelism by not implementing it yourself, just calling NumPy or SciPy, and they can go off and do parallel work for you. Again, it will still be inside a single node, but you can use up to 128 workers on ARCHER2, so you can get a reasonable amount of performance improvements. You can also write your own native code interface, so you could write code in C or Fortran or C++ or something else, and then write a binding between Python and C, and do that Python in the lower level language, and then pass the data and backwards and forwards, and then use a lower level language to do the parallelization and communications. And then there is an MPI for Pi library, which gives you a direct interface into doing distributed memory across multiple nodes using Python, using exactly the same sort of configuration and functionality we would do in Fortran or C or C++. If you're interested in that last one, then we've got a whole set of lectures on MPI for Pi. You can have a look in the ARCHER2 Python course and have a look at that in more details. No, I have not myself used ZMQ, but there are a few other libraries out there which will allow you to do multiprocessing, parallelism, those kind of things there as well. And I've not looked at the Pi ZMQ on ARCHER2, but we could have a look at it if that was useful. Let me know. So that's a sort of whistle-top tour of parallelism that's sort of the default approach in Python, which is, yes, you can do parallelism, and you can either do it like we do it in other languages with MPI and just call into that, do a direct interface into it, or you can do built-in things into Python language, but they tend to be a bit more restricted and not necessarily give you high performance or kind of high performance we'd like on a system like ARCHER2. And then the other approach is what people are commonly using nowadays is, and there are a few of them, but Dask is one of the most popular ones, and that's use an external library which provides you some more of this functionality, but in a way which is more natively Python. So Dask is a external library to Python, but it's been written to give you parallel computing functionality for your Python program. And it's built around this idea of task scheduling. You split up your things to do into tasks, and then you can let the Dask library run those tasks for you. So you don't have to tell it how to do that. It will go off and run the tasks for you. And you can set it up in such a way that it can run the tasks just on a single node, or it can use many nodes on a system like ARCHER2. And this has the benefit that you get the parallelism, but you don't have to do the low-level programming work that we may have to do in MPI for Pi or in a low-level programming language. It's quite like the multiprocessing approach in the Python that we saw earlier, but again, you don't have to manually specify how things are run and how data is passed backwards and forwards. There is some built-in functionality which handles a lot of that for you. Dask has two main parts to it. The data collections and types, which are sort of the user-facing code, where the bits you can use inside your program to give you functionality. And then the task scheduling functionality with the parallel backends, which is used under the hood to run the things that you want to do. So from this picture's point of view, the things on the left-hand side, the collections, are what we use inside our programs. They're our interface into Dask. And then the middle and right are what Dask does automatically for us. It takes what we've specified, it turns it into a graph of tasks to be run, and then it runs those in various ways. Now, it's worth saying that this is not a new approach. It's not an approach that's exclusively Dask-based. There's been lots of task programming, task scheduling libraries in the past, even in parallel computing, even on systems like Archer and its predecessors. We've been working on these kind of automatic parallelization and distribution approaches for a long time. There's some famous ones that come out of Barcelona Supercomputing Center, OMPSS and things like that, which do exactly this. But where Dask has some leverage is that it's easy to use from Python, so it's designed from a Python perspective, and it also has some nice interfaces to existing libraries. So that means it works well if you've written NumPy or you've written Pandas data frames, then they can easily map onto Dask without you having to do very much work. So what it does, as I say, is it splits work into tasks to be undertaken, and then it schedules those tasks on available compute resources. It does by default, it does what's called lazy execution, which is actually, it creates a task graph, but doesn't run it all at once. It runs things only when they're required. And this is because when you're building task graphs, you won't actually know how to optimize it. The runtime doesn't know how to optimize the overall graph until right at the end. And then it can do things like get rid of bits of computation it no longer needs because the task graph can be optimized. You can get rid of things. Now, the example I've got here, there's no real way to optimize it, right? You're just summing up a bunch of numbers and you need those numbers and you sum them up and you produce a result. But in more complicated graphs, you can get rid of temporary data and temporary solutions and all sorts and things like that. So Dask has this model where it doesn't run things until you tell it to, so that you can get your final graph, and then it can optimize it, and then it can go away and run it. And that's what we mean by lazy execution. Is there any questions on this overall model before we go diving into of Dask? Okay, so it's a good question. You know, is each image a Python? Oh, hang on a second, that's not updated. Here we go. Is each image here a Python object? So this is just an example. Each image here is each part of this image is not a Python object necessarily. Each part of this image could either be an object or an operation on that object. So you don't care about this graph really. Dask builds this graph for you. But what it does, it takes all the objects and all the operations you've specified on each object and then builds it into the dependency graph, which says which operation depends on what object to get your final result. And then it glues them together into your overall program you want to run. So that's what it does. You specify it. Now we'll see in the next slide how exactly you do that, but basically you tell it what code to run. It then takes that code, analyzes all the inputs to that code, and works out a graph like this. So Dask has three main built-in data types. It's got an array, which you can think of as a NumPy interface. It's NumPy array with a special feature that it can handle arrays that are bigger than the memory you have available. So it can do some distributing of arrays across workers to let you process arrays that are much bigger than you could fit on a single computer. And that uses functions like zarray, if you've ever heard of it, the zarray library, under the hood to do that kind of thing. It has a data frame, which is very much like a Panda data frame, and that's this sort of Panda interface there. And again, it can handle data frames that are bigger than a single computer can hold, although Panda can do some of that as well. And then it has a more generic data structure called a bag, where if you're not doing NumPy or Panda things, you can build your own data structure you can use out of general Python types or your own types. And then it lets you distribute all these across compute nodes, but still have them processed as if they were being done on a single computer in serial. You can also, so that if you use this functionality here, Python Dask will really do the parallelization and the graph building for you. It does, however, give you an interface to do some of that stuff yourself. So you can construct custom graphs using this Dask delayed interface, where you can put things together. And you can also use something called the Dask futures interface, which lets you specify tasks and get them, so build your graph that way. Okay. There is lower level functionality to let you send and receive data between all the workers and do queues and variables and locks and barriers and all that kind of stuff as well. But that's more involved Dask work. Okay, what does this look like in practice? Well, if we look at the Dask array, each worker's part of the overall Dask array is just a NumPy array. So if I create a very large array and distribute it across workers, underneath the hood, they'll just turn into NumPy array chunks. And then there's some code in the Dask which puts all the communications together to distribute the work across those. We've got an example piece of code up here where we import Dask array, and then we create a random array. This one here is 10,000 by 10,000, and we specify in how we distribute that across workers. So I want to distribute it in chunks of 1,000 by 1,000. So that, unless my math fails me, should give us 100 workers, or chunks for 100 workers. We don't necessarily have to use 100 workers, but it gives us a scope to use up to 100 workers. And then there's lots of functions we can use here, just like you would have in NumPy. So you can create random arrays using binomial or normal, Poisson, or random distributions. You can create them from NumPy arrays. You can create a Dask array from a NumPy array. Or you can create it from files. So you can read in groups of files into Dask to create a Dask array using some of these interfaces here. There's also functionality to let you put together multiple arrays into a single one. Also you can create Dask arrays from delayed functions, but that's a bit more, it's a bit more in-depth there. Now it says here, just reminding you again here, because of the way tasking works in Dask, everything is done lazily. So we still have a lazy evaluation. So if I run this code up here, x equals da random.random 10,000 by 10,000 comma chunks 1,000 by 1,000. After that line, that x line there, in a normal program, the object x would exist and have all the data in it once that random.random function is returned. In Dask, unless you force it otherwise, that X object will have been created, but this data set here will not exist yet. So the object will just be a definition. I'm going to be created in the future. I'm going to be created of size 10,000 by 10,000 and in chunks of 1,000 by 1,000. But it's still, until we do some work on that and need a result from it, it won't actually exist. So it doesn't happen till now. Then Dask array supports a whole bunch of NumPy-like functionality, so arithmetic, reductions, tensor contractions, axis reordering, slicing, indexing, those kind of things. If you have a look on the Dask website, there's a much more detail about exactly what is supported, but a lot of NumPy functionality has been ported into Dask functionality, so you can take two arrays and add them up, even if they're 1,000,000 by 1,000,000 across lots of workers and those kind of things. There are some restrictions, and these change from time to time, so these might not be 100% up to date. But a lot of the linear algebra functionality in NumPy has not been implemented, so you need to check if you needed some of that. It doesn't really like arrays with unknown shapes, so it likes the distributed array, understandably, to be reasonably well defined before it's used. And there's not particularly good support for sorting of arrays or to list functionality. You probably wouldn't ever want to do to list anyway, because you don't want to bring it down to a single worker, most of the array down to a single worker, because you'll probably run out of memory. And iterating across a Dask array can be very inefficient. It's not generally the way we use them. So that's the sort of basic introduction. Effectively, it's just NumPy with some restrictions distributed across lots of workers, and it should work as normal. If we look at the Panda lifestyle functionality, it's done in exactly the same way. The overall Dask data frame is just made up from a bunch of individual Panda data frames stitched together. And then they have very similar functionality, except if you'll see at the top here, we don't tend to specify, you don't have to specify how you split this up across workers. Okay, so if you don't have to do that, it can do that for you. But in the NumPy stuff, we generally have to. We want to specify how we're splitting it up. In the Dask data frame, you don't necessarily have to. You can specify the blocks you want to distribute across workers. And then you can create this in lots of different ways, right? So from CVS files, from Parquet, from HDF, from SQL servers, those kind of things. From delayed objects. You can create a data frame from a Dask array and from the other data structure as well, from the data frame, from a bag, sorry, and from other objects. And then just as pandas will specify, will give you a lot of functionality, you can also do very similar things on Dask data frames. So you can do independent operations such as element and row wise, locating individual features, aggregating, discovering data, group bys, duplicates, joins, element-wise operations, averages, those kind of things. If you're going to do group by operations, you probably need to do some data reordering, where you set an index and you apply those kind of things across there. But that's the kind of functionality you get from the data frame, with the caveat that setting new indexes on unsorted columns is expensive. As you can imagine, you've got to go across all the individual data frames in the group and do that work across them. And also on doing things on other operations on, so because setting that index on the unsorted column is expensive, any operations which require dirt are also expensive. So things like group by and join and those kind of things are expensive. The Dask data frame doesn't support for full Pandas API. And things that were slow in Pandas, so in the normal Panda data frame, like iterating through row by row, rather than using the built-in functions to do that, is also going to be slow on Dask as well. But there's much more detail again on that if you want through the Dask website. And then the final thing we saw is a more generic configuration or more generic data structure which lets you write your own things. So this is called a bag. And this is like a list or a set, Python list or a Python set, an ordered collection of data with repeats. A bag is immutable, so you can't change it once it's created. You can create new versions from it. And then there are map, group by, filter and fold and other functions you can run on this unstructured data. So it's pretty good for parallelizing simple computations on unstructured or semi-structured data, text files, data files, user-defined Python objects, JSON records, those kinds of things. It is built on top of the multiprocessing functionality in Python, so not the threads, which means it can be a bit slow in places, but it does work and it can distribute across large numbers of workers. And you don't need to care too much about this, but you can create them from sequences or from text files or from data frames. You can do operations like accumulate or select any or select all or count or max, min, sum, those kind of things. So we've got examples here where we create a data frame, we import from a sequence, and then we add them up. And you can see these functions here now. We've not gone through them all, but this is now a full Dask sequence where we create an object, specify how it's parallelized off a number of partitions here, and then we're going to run an operation on it, and we've put a function on the end here called compute. And that's what actually causes the operations to be run. And it's no longer lazy by this point. You're actually going to get your data at the end of that. Up till that point, nothing has to have been computed. But once you call compute, you get that there as well. I didn't have examples of that before, I don't think. No. You can also do custom operations on it where you define your own function. and then apply that to the bag itself, the bag of data. So you can apply this filter function here on a bag. So we've got a bag here, and we are applying the filter, which is even. It's a function I've designed, which can divide something by 2 or modulate it by 2 and see if it's 0. So it'll also tell you if a number's even, and you can run that on the bag of data itself. You can do the same thing with lambdas, right? So you don't have to define a function. You can use a lambda, so an in-place function, and do exactly the same kind of thing there. But we just remember that bags are immutable, so we can't change them. And in general, arrays and data frames are faster than bags because they build on optimized functionality in the hood, whereas bags are designed to support generic functionality for any possible combination of things. So they're less efficient. It's also worth bearing in mind that there's the group by operation that we show up here. It can be pretty slow, but there are other ways of doing things which can be a bit more efficient. So there's something called a fold by operation, which is actually a reduction and then a group by, which is sort of a split data up, apply the function, and then combine the data back up, which can be faster than a group by. So fold by is a way of doing a faster group by. So that's the built-in functionality you have from Dask. That's the built-in data types you get given. There is also, as I mentioned at the beginning, a function to build, or functionality to build your own graphs. So do direct task generation, so you're not relying on inbuilt functionality from the data frame library or the array library or those kind of things. And that's the examples we've got here. So we use a delayed function. We can either do a delayed function or use this annotation, so this at dask.delayed functionality, to tell Dask these are the things you need to put together into a graph, and it will go off and construct those graphs for you here. So we've got an example here on our right hand side. The sort of first example on the left and right hand side, we've defined 3 functions: increment, double, and add. And we've then defined a data array, or list actually in this case. And then we go through every element in the list, increment it, double it, add those 2 things together, and append it to the output. Okay, that's what we want to do. And then if we wanted to parallelize this, there's 2 different ways we can do it. Directly below we see the first one, which is we import the Dask library. We have all those definitions we had before. So we do the increment, the double, and the add definition. And then in that loop, instead of just doing the operations, we put them in as delayed operations. So we say dask.delayed, name of a function, inputs to a function. Dask.delayed, output.end, dask.delayed of the sum as well. And then we do a dask.compute at the end, and that says, okay, now create the graph and run it. So there we are marking each function. We are wrapping each up function in each function call in a delayed function call, and that will add it to the graph. Or on the right hand side, we've got doing the same thing but using this decorator instead. This decorator is a thing which, when it's parsed by the Dask library, it will say, okay, create every version of these function that's called as a delayed function. And then we can see we don't need to change the main body of the code. All we have to do is put a Dask delayed on the sum at the bottom here, because the sum is not a function I've defined, it's one I'm using from the standard library, and call a compute at the end as well. And both of these do exactly the same thing. I mean, the reason why you'd want to do the left one and not the right one sometimes is if you had functions that sometimes you wanted to delay put into a DAS graph and other times you didn't in the same program. And so the one on the right, you're always creating DAS graphs from those function calls. The one on the left, you're manually specifying which function calls you want to put on the DAS graph and which you don't. You ought to also be slightly careful when you write this. So if you see my examples here on the left-hand side, das.delayed brackets f brackets xy is not the same as dask.delayed brackets f close brackets open brackets xy. So the delayed, it can work in both ways, but it expects the first brackets to be the name of a function and then the second brackets to be the arguments you pass into the function. In the top one, it's going to run f of xy immediately, not put it in a graph, and then it's going to take any output that came from that and then store that separately, put it in the graph, and then when it runs the graph, have it later. Whereas in the bottom one, this is you actually saying, okay, I want to create this as a part of the graph and run it when the whole graph is ready. And finally, there's a slightly newer version of this library which lets you do more complex things, which is called the futures library, and it doesn't necessarily delay task execution. So you can create your own tasks, you can run the functions on them, you can move data backwards and forwards. So here's an example of the same program we saw before, but in this case we are manually creating this as a futures graph and running it exactly as we would like to, as we saw before. So here we are manually working with distributed workers. So we have got to create a client, and then we can submit each function with an input to the client, and it will run them, and then we can get the results back from that and use it later in a range. And it lets us do more complex things, so we don't just have to pass in single arguments, we can pass in ranges, and it will map that onto 10,000 1,000 different workers, which will each do a separate result. So there's a bit more flexibility there. But I would just say that these two here, futures and delayed, and even bag really, are not the things that people usually use in Dask. It's data frames and arrays. That's the core functionality, and that does all the graph stuff for you, really. By default, Dask is generally default to this shared memory parallelism that I talked about before. So this single node threaded based parallelism. By default, it will try and use all the cores it has available to it, and it will, that's what the data array and the Dask array and the data frame do. As we said earlier, the bag is generally defaults to multiprocessing. So that's not quite as true, but it will still try and use all the cores it has available inside a single node. We probably want to, if we're using Dask in earnest, have a bit more control over that. And so there's a whole set of library functionality to let you specify what kind of parallelization is used and how it works, how many workers it has, and those kind of things. So we can see here you can specify or you can modify how things are run. We can specify what to use, whether it's a thread worker or these multi-process workers using the scheduler thing here. We can have, but we can do more advanced things by using a library called dask.distributed, where we can set up a client and we can do more multi-node Dask work as well. So the standard Dask stuff will be restricted to a single node, but we can do distributed Dask where we can work across multi-nodes. And it'll also produce some nice dashboards like this on the right hand side here, where you can see your tasks running, you can see your workers, you can get some profile information about all those kind of things going on. So it's worth noting, it's pointed out in the exercises, but the Dask distributed library does not the default install of Dask. You have to install a second library on top to get it, but it's pretty easy to do. We can do that scheduling globally for everything. So we can just do a dask.config.set. You can do it in a context where you can say anything under this part of this with statement here will use this kind of scheduler, or you can do it on a per run basis, per function basis. You can specify how those things are run. In general, you probably don't need to get down to this level of doing very specific scheduling. You can just specify for your whole program, this is what I want to do. And you can also control inside the program how many workers it uses. So you don't have to use all 128 cores on a node. You can specify how big a thread pool or how many distributed workers you want to use. Getting into much more detail then, if we want to then go across multiple nodes, like we probably want to do on a system like ARCHER2, then there are multiple ways of doing that. But really we're going to look at using the Slurm approach here, the Slurm cluster, because that's what the Dask job queue Slurm cluster is, what we have on ARCHER2. And we also could use Dask MPI, which builds off the MPI library to do similar kind of thing as well. Lots of complexity here. Again, you don't need to worry too much about it, in the sense that we have it all installed on ARCHER2 and we have documentation on how you would generally run it on ARCHER2. Some guiding principles for using Dask is, first one is don't use Dask if you don't need to use Dask. So NumPy arrays, Panda data frames, all these kind of things will generally be faster by themselves without Dask if that's all you need. So if you only need a single node, if you don't need more memories in a single node, then you don't need to go up to this fancy parallelism because it will add overheads. Chunking and granularity is important for performance. So how you split your data up across workers and across available resources. If your chunks are too big, then, you know, if I had a million by a million array and I split it up into 4 bits, that's probably not enough parallelism because I've not got enough workers to efficiently process it. But if I split my arrays up so each worker only gets one element of the array, that's probably too much parallelism. I'm going to be a large overhead for that. So there's a bit of tuning to do when you do a Dask parallelization to try and work out how big your chunk sizes should be to get you the best performance on a given system. The fact that Dask is lazy is a good thing in most of the time, because it means that the task graph can be built and then optimized at the end and then produce a sort of minimal runtime thing that reduces the amount of work that needs to be done. You still need to call compute at some point to force evaluation of a task graph. And sometimes if you're using Dask for very big programs, you can't build the whole graph because it's just too much. The graph gets too big for the Dask engine to process. So you may have to do temporary subgraphs. So you have to call compute every so often to do up to a certain point, and then it starts again. If we go in for very large Dask parallelizations, it can be good for to mix processes and threads. So if I wanted to use 100 nodes on ARCHER2, I might want to run 8 processes, and each one of those have 16 threads, and mix that up by controlling some of these schedulers here, because that can give me better performance. It reduces the amount of workers involved in each level of communication and can improve kind of things. To get good performance on Dask, we probably want to load our data with Dask rather than loading our data into NumPy first and then getting it into Dask, or rather than loading it into Panda and then loading it into Dask. It's sensible to do, if you're doing some work on a data set and then you're reducing it to a smaller size as part of that work, it's probably sensible to then store that back as your Dask object rather than keeping the larger data set if you no longer need it, because that can reduce overheads as well. On ARCHER2, the Dask we have is in there in the Create Python module, but by default it's only the threading shared memory backends. Okay, so it doesn't give you a distributed Dask, doesn't give you things that go beyond a single node. You can install that yourself though using these commands here. So we load up Python, we set our user base, we export our path, and then if we just do Python pip install user Dask distributed and then Dask job queue, that should install it for you. There is also a restriction that often on a system you would install Dask and then you would run Dask on the login nodes, and that would start jobs on the compute nodes. But that's not the way ARCHER2 works. We have to actually launch our Dask jobs from the compute nodes as well as running the workers on the compute nodes as well. So what does that mean? We can run a normal Dask program, so single node Dask as normal, just as we've seen in previous batch scripts. So we've got here just a normal batch script or an interactive run, and that will run Dask just fine. But if you want to do a distributed job which goes across multiple nodes, then we need a bit more code in our Python. So this is all Python code which would go in my program. The top few lines are just setting up the Dask distributed client to set up all the workers in the Dask program, and then you can create an array and run that across those workers. So this bit at the top is a bit what we call boilerplate code, where you have to do the configuration of Dask. And what you can actually see it's doing here is it's going to set up its own Slurm job and run that for you. And that means you've got your Dask client at the bottom here, and you will create a Dask program, run it, and then that will go off and set up a new job to actually do the calculation itself. Now, this all looks a bit complicated, but once you get it set up, it's pretty straightforward and will work reasonably well. You can even, with a bit of work, connect to the dashboards, because these kind of pictures you can get directly off the system itself as well. So that is possible. So we have standard Python on ARCHER2. We have lots of optimized packages for numerical libraries, those kind of things. And if you want to then go to more parallel, large-scale things, then you can do it with standard Python approaches inside a single node, multiprocess or threading, with the limitations that they have. And if you want to go beyond a single node, then Dask is a good place to start. You can use it on a system like ARCHER2 and elsewhere. You know, it's a widely used framework, and it will give you relatively good performance, provided you configure it and align it with the hardware we're using efficiently. You know, Dask is very much a task scheduling framework. It's very similar to Hadoop in some ways, if you are ever around in the Hadoop era or are still using Hadoop. So it's a sort of similar approach to that, except from Python. Just about on time. Has anybody got any questions about Dask or about Python and Python parallelism in general? If not, then there is a exercise now. Let me go and share that. But it's exercise 4, I think. Yeah, exercise 4. Let me stop sharing this window. And share that window. And you'll see there's a module load create Python. And then this first bit here, the first bit at the top here is just running the standard Dask that is available on the compute nodes through CreatePython. And you can use the data frame as well. If you go into there, there's a surveys.csv file to use, which is in the, if you go into ARCHER2 data science exercises Dask, you'll find the files in there as well. So that's part of the thing that comes out of the repository. The only thing to be aware of for this data frames one is this visualize functionality, which may not work for you depending on whether you have certain libraries installed. Don't worry about that. If the actual displaying of the data doesn't work for you, it's not necessarily important. And you can play around in those two. This is just on the login nodes here, right? You're not doing anything particularly onerous, so that's okay. You can play around with different block sizes, and you can play around with the bags, but then you can write your own functionality. So this Dask delayed functionality, like was outlined in the lecture, and then there's a Mandelbrot calculation here, which is a function which can be trivially parallelized or task parallelized here. So you can turn that into something which runs through Dask. Have a look at that. If you're really struggling with that, there is a solution for it in the Dask mandel.py file, which shows you how to do it. And then we can also calculate pi here. Again, another thing which splits up into tasks and run that across workers. So that works quite well. So have a look at it, try it out, and try running on the system to see how you get on. And let me know if you have any questions. Or should I say when you have any questions, because you probably will have. Hi, so if you're asking, do you have a place where we can just copy the source code from? Two ways you can do this. One is you can just clone the repository onto ARCHER2. So if you just run this command in your terminal and in your work file, it will get you that code. If you'd rather just copy it from somewhere local, then exactly the same repository is also sitting in here on the ARCHER2 system. And so if you go into there, there'll be a directory called there's this directory here, which you can copy the code directly from as well. Okay, we've got a bit of another break here for half an hour between now and 4, but feel free to keep working on the exercise. I'll still be around here till 4. Keep going through the Dask stuff. Any questions, keep dropping them in the chat. That's fine. And then we'll pick up with an R lecture at 4 till 5. Probably won't take 4 till 5, and then practical to finish. But yeah, keep it the questions with any issues with the Dask one. Just a quick reminder, if people are heading off, it's just fine. There will be a feedback link which gets circulated and will be on the course web page if you want to provide feedback as well. So that would be useful either way. Okay, so that was, we've looked at Python and Dask in a bit more detail. And now we can look at R, which is obviously another tool for data analysis and used heavily by data scientists, to see what, in a similar way as we've done with Python, how would we use that on ARCHER2. And the same thing applies, as we said before, for ARCHER2 and Python. There is no real difference in the core R functionality on Python, on ARCHER2, compared to on any other system. We've got the same setup installed, same core libraries. It's some of the underlying numerical implementations should be targeting the career libraries so that they're efficient. And then we just need to look at how would we parallelize, how would we scale up if we didn't want to just run one R job or lots of small R jobs together, which we know how to do by using the batch system. How would we scale up to doing larger jobs, large scale parallelism with our whatever approaches we can use to do that. We've got an hour scheduled for this lecture and then half an hour practical at the end. In reality, this lecture doesn't usually take that hour, so we have a bit more time for practicals at the end, or you can leave early, or you can keep doing the Dask Python practical and try that out as well. So I'll circle back to some of the other practicals we've been doing. So this is very similar to what we would see in Python, as well as in R and in other languages as well. Why would we want to do parallelizations? Why are we interested in doing parallel functionality? Here, what are the reasons that we might try and do this? And they are because my program takes too long, so it's too much computational work. An individual data analysis or script in R is taking days or weeks or months, and I want to speed that up. I've got too much data to process, but my individual program is quick, and we've already seen how we can tackle those kind of issues, and just running multiple copies of R at the same time will work. But the other classic one is my data is too large, so I've got more data than I can fit in the memory of a single computer. I need to parallelize across that. Now, R has lots of functionality to do these kind of parallelizations, this kind of parallel functionality, from implicit and explicit parallelism through to pre-existing parallelizations of particular applications, batch system integration, native code interfaces, and big memory functionality. There's quite a nice overview of it on the High Performance Computing Project webpage here, which will give you a bit more detail over these kind of things. But we'll go through these in a little bit more detail. What I should say is that this is not meant to be an exhaustive list of parallelizations or possibilities for parallelizations. There are lots of different ways you can do this. There's lots of external libraries and packages for R to do this kind of thing. This is just an example of some of the common ways of doing this. So there are ways inside R, rather than using the batch system and using the array jobs and other things we've seen below, to do trivial parallelism, which we could call, used to be called embarrassing parallelism, which is effectively run lots of copies of the same worker just on different data sets. And there we can use the apply functions and the map functions from inside R to do that. There's also loop-based parallelism, so for each, where you can distribute that across workers as well. And then there's more heavyweight or more functional threaded parallelism using something called DSM, distributed shared memory. That's a library. And then if we want to go across distributed parallelism, so using multiple nodes, using multiple servers at once, there's a number of different ways to do that. There's a library called Parallel. There's a library called Snow. There's an RMPI library, which is very much like the MPI for Pi we saw for Python. It's a native implementation of a message passing approach, but for R. And then you've got PDBR and for each, which will also distribute across workers as well. So there's a lot of parallels here between the kind of things we're talking a bit about in Python and in Dask and what's been seen here. There's no real new ideas for parallelization. We can parallelize inside a node, we can parallelize across nodes, we can distribute loops, we can implement direct communication, or we can do some kind of task scheduling like Dask does. If we look at the sort of automated parallelism, and this you could think of as like NumPy for R or SciPy for R, libraries that have built-in parallelism which will automatically use extra workers if you have the hardware available. Some of the inbuilt things in R will do this for you already. So what we would call the underlying mass libraries, because the Cray version of R here has been set up to use them, it will do that kind of thing there. So it is an example here where we're taking two matrices and we're doing matrix multiplication or some kind of matrix operations on two matrices. If we use the data table library here, we can see that when we load up the data table library, it will say, actually, I'm using this data table library and I'm going to use 128 threads. That means I'm going to use 128 workers on this node because I've got access to that, and away we go. And actually, by default, R will, with these functionalities, try and use all the workers that are available. So if you run R on a compute node with a script and it's doing some of this built-in functionality, it will try and use all 128 workers at once. You can control that though, so you can use this OpenMP numthreads, OMP numthread functionality before you run your program to specify the maximum number of workers. So here, if I run OMP numthreads, if I set that in my batch script or at my command line before I run my application, then that when we actually load the library, you'll see actually now it's only using 2 threads. So it's picking up what we specify at the command line here and saying, I will apply that. And so that can be useful because you may have access to 128 workers, but it may not be the fastest way of using the system if you try and use all of them. It just may add overhead and not improve things for you. So that can be useful to be able to control that kind of parallelism there. R also has some built-in functionality which will give you what I'm calling here trivial parallelism, which means you can run the same function on lots of different workers. And so here we can see an example R script where the same code is executed in lots of different places. And then you would need some kind of mechanism to pass in a value to specify a seed. So it's maybe not clear what's happening here, but in the top bit here, I've got, I'm reading in my R script from the command line. I'm going to read in a value. And then here I'm going to set up my random number generator to use the value that was passed in. And then I'm going to read a data set. I'm going to run k-means on that data set to cluster it, and I'm going to print out the result. And then down here where we run our R script, that one there, that one is what's been passed in here to specify the seed for the random number generator, which will then be used to initialize the k-means algorithm to do an evaluation of the clustering. And then I can pass this into Slurm array jobs, pass in a different number here for each array job that's run automatically, and then I can run, 64, 128, 256 workers who are all going to run the same k-means on the same data set, but from different initialization points, from different seeds, random number generator seeds, which will let me do some very trivial parallelism, and I can run all of these at once and get my results back quicker. But I'm not doing anything clever here. I'm not trying to modify how the program works. I'm not going to try and modify the actual underlying communications or adding communications or anything like that. I'm just going to specify in this instance, with the way we configure our random number generator is going to be different for each one of the workers, and that might be useful to me for my statistical analysis of what I'm doing. Now you can also do cleverer things where you could pass in a different data set for each worker by using the number that's passed in here to select an entry in a file which lists all the data sets, and you could do different things there. But that will, there's not much, this is not using any parallelism inside R here. It's just reading command line arguments, running it with a Slurm array jobs to pick up different inputs as we go along. And a more still relatively simple parallelism, but using more functionality inside R to do parallelization, we can actually do data set decomposition or data decomposition inside our R program, where we take the full data set and split it up across workers and then give each worker something to do. And so here's an example here. It's more complex. We have to change our code to be able to do this. But we partition our data, so we follow the split, apply, combine approach, where we split our data into groups, apply our operations on each group, and then combine the results at the end. So in the past, we would have had something like this: reading the data set, apply co-means here, and print out the results. And here, so instead of doing 100 iterations of this, what I'm going to do instead in the parallel version is create a parallel function which applies k-means on the data set with a given number, this end start, and then use the R function lapply, left apply, to actually say, okay, for this function, run it 4 times and pass in the number 25 on each time you run it. Okay, and that's what you're doing here. So you're creating 4 versions of this that can be run independently, and then we use this sapply function to then get the data back from that result, and so create a vector out of that. Now, in its first instance, that's not actually going to do anything in parallel, but it will set us up so that we can do parallelism in the future, because it's creating work for different workers to do. In the first instance, by default, it may not actually run them at the same time concurrently, but it may just run them one after the other sequentially. You can also do a similar kind of thing where you produce, instead of a single answer as the result of your function, you produce a list of answers as the function. And so you can see lapply of this function here. This is the function we've defined. Will produce a result for each time it's produced, and that will return a list of lists or a vector of vectors in this scenario. And we can then do a call at the end to combine the results into a single vector like this. So it takes it and pulls out the data. So we may have to do a little bit of massaging of our final results to get them back into a form that is useful for us to be able to use. And the nice thing about this approach is we can do this and it doesn't change our program. It doesn't necessarily make it parallel at all. But then we can apply some different libraries to turn that into a parallel function that works. So in this example, we can use the MC apply, multi-core apply, to take what was given there and turn it into something that will run in parallel. And so we have we're importing the parallel library, as we can see here. We're reading the data set, we're creating the functions, that's all happening without any parallelization. And then we use this MC lapply, which then goes off and creates some workers. It'll create 4 workers and run those 4 workers on it. We're still talking inside a single node. We're still talking the reasonably simple parallelization, so there's no communication between the workers. We're doing things separately there, but everything else stays the same. We haven't changed what we're doing, except we've changed what function we apply there. That uses processes rather than threads, So that means, theoretically we can go across multiple nodes, but not with this specific setup. And we can control how many workers we want to use here. So now we're not using this OMP num threads to control it. We're using MC cores, and we can specify that. You can also specify that inside your code, right? So it's not quite as flexible, but you can specify it in there that you can do it from a programming point of view. It's also, if you have a look at it, there's more functionality in there to do things like schedule and load balance. So if you're not evenly dividing the work here across all the workers, it can do a bit more clever scheduling to try and load balance to make sure all the workers have a similar amount of work to do as we're going on. And that's important because in this example, it could be that this splitting up by 25 here, it perfectly gives each worker the same amount of work. But in a lot of cases, a lot of algorithms, the work is a bit variable depending on exactly what part of the problem you're looking at. There is also, in the same library, in the same parallel library, there is this MC parallel and MC collect functionality, which lets you gather data together and collect the results. So you can run sets of work in parallel using MC parallel, and then use MC collect at the end to gather that into a single overall vector or list or something of data there. And this can be really useful when we're processing data files, large data files, where this example below here, we're reading in a data file. We want to extract data out of that. And so in parallel, we want to sort it and get the unique features and then get the length of that. And then that gives us a unique thing. And then we can pass that. We can also at the same time do a median of there and then collect them together into a single data structure. And that will go off and do some parallel work for us there. So the parallel library will provide you sort of a bunch of functionality to both parallelize applying functions and with some built-in functionality to parallelize other things as well. There's also a for each library which will parallelize loops, either implicit or explicit loops for us here. So we can do exactly the same thing here, where we read in the data set. We're still doing this function where we do calling k-means, but here we're doing it as a loop. For each, and this is the iterations of a loop, do this, and everything else pretty much stays the same. And then we can use that with other libraries, such as the do multicore library, to give us a backend which will give us do parallel, that for each, and then that will go away and run across a bunch of workers as well. So just like we saw the apply approach breaking our code into something we could then run in parallel, the for each approach does exactly the same thing, sets up the program where we can break it into something that can run in parallel. And so that's a lot of the functionality in R is about either parallelizing functions or parallelizing loops, such as that. And then you can then look into expand it to run on across multiple nodes or inside a single node with a specific library which gives you that functionality. If we want to go to that multi-node context where we want to use many or at least more than one compute node on ARCHER2 for the same job, we then need to bring in a library which provides that functionality for us. And in this context, we're looking at the Snow library. And Snow gives us this cluster and parallel lapply functions, which will distribute work across workers, even across multiple nodes. So what you'll see here is, again, our function is exactly the same. Our reading the data is in the same. But here we're making a cluster. and that cluster is built on MPI. There's different ways of doing this, but this can build off an MPI library. So that means we can use the same libraries that are used for high performance communications on computational simulation programs on R as well. And that makes it easy. We don't have to have something that manages communication for us. It's all done through MPI. I have to distribute the data that I've read in to my cluster. So I've created a set of workers. I'm distributing the data to them, and then this parallel apply will then run on this cluster and produce the results that we want. Okay, the data has already been exported, so all the workers have a copy of the data, and this may not be the most efficient way of doing it because you may not want to give everybody a full copy of the data. You may want to partition it, for instance. But then after that, it's all fine. We can use it as normal, and at the end, we just shut down our cluster, finish the MPI, and that should go off and work. And similar functionality also exists, not just for the function-based lapply stuff, but for the loop-based, for do parallel to go across MPI clusters as well. So here we're using the library doSnow, which builds off the same library as Snow before. So we make our cluster, we register this cluster with doSnow, and then we call a doParallel, and it will automatically distribute that loop across our workers again. So we see exactly the same thing, but we have a mechanism to do it for loops as well as for functions. It's also possible in Snow to run more complex things inside the parallel cluster. So we can write individual functions and call them on the cluster, those kind of things. So we can set up and run parallel R programs that have much more functional configurations, not just using things from libraries as well. So we can do that kind of thing as well. How do we get up and running with something like this on ARCHER2? Because Snow, the underlying, so everything else we can pretty much just install as standard. But once we start going across multiple nodes, once we start doing distributed parallelism, we really want to be able to install a library which is going to map down to our Cray MPI library. Here we're going to use the Snow package. If we're going to install things on ARCHER2, just like we saw earlier in the day, we need to specify that we need to specify this R-libs user function environment variable to tell it where to install things. But we often also need to, when we do this for a start, set up R so it picks up the Cray compilers, or at least the system compilers sensibly, and we do this just by following this recipe here. We can load our Cray package, the compilers we want to use, and then we should just be able to build this here. Now I've already installed RMPI for the Snow package on the system in some way you can get access to it, and so you should just be able to run this command and it will build it for you. And then when you've done that, you can install Snow directly on top of your R package. As long as you've set all this stuff up here already, then that should pull it down and install it for you. In terms of then running it, how do we create a batch script and run the parallel application on the system here? Well, we can use a helper thing that Snow provides, or RMPI provides, which is a little program which will run your application for you. So our standard batch script is the same as normal. We then load the Cray R library, initialize our environment variables and paths, and then we just do srun MPI Snow, RMPI Snow, pass in our application, our program to it, and then that should just run it as normal for us. There is a lot more you can do. There's a lot more configurations and functionality that is available for it, including integrating with things like the Slurm environment to pick up the number of workers we have automatically. So that's what we're doing here. Nmax equals as numeric system getting Slurm nproc. So basically this is just saying how many workers do I have when I run. I can set up my MPI cluster, and then I can do more complicated things inside the thing here as well. So I create a function which does a bunch of tests. I export a data set out. So this is a function which is going to be run in parallel to create my data set. And then I can apply that function to the cluster like this. And it will go away and it will run this function on the workers that it has available with as many workers as I've found in the system, and it will go away and create my data set for me, and then I can go off and query that data set and produce some results from it and shut down the cluster as well. So we can do more complicated things than just using the lapply and for each. It's possible to write much more complicated functions and define exactly how you map them to a cluster. But in reality, it's doing very much the same thing, which is you have a set of workers. You need to define some way of mapping your task or your data to those workers, and you can then get it to run it for you. And that more complicated functionality is running exactly the same way here. So we just write that into an R script and then just run it with this RMPI snow, and that goes away and does what we want to do here, produces our results, and we'll produce the data we need. So R has lots of mechanisms for doing parallelization, either inside a single node or across nodes, either using functions or loops, or more complicated structures as well. They're all up and available for you to do, to use and do your work on. There's no one good way. No, this is the only way of doing parallelism. There's lots of different ways depending exactly what your code requires. Reality is that doing lots of small loops in parallel probably isn't going to give you good performance, because the cost of sending data to and from the workers, or the cost of starting up workers and stopping them, is going to be high. But if your loops are big and have got lots of work inside them, then the looping mechanism for doing parallel R can be just as efficient as running functions everywhere. But it's worth bearing in mind that you can control directly how many workers you'll use, and whether they're threads or processes or going across nodes, by the way you set up the R and environmental variables that you export when you're doing that kind of stuff. And the version of R we have should be relatively optimized, at least for the basic parallel stuff. So the basic matrix vector operations through R should call down and should use the underlying maths libraries and underlying setup for the Cray system in general. So for a lot of applications, you can get away with doing quite a lot just by using what's built into R and running that on the system, on the nodes. We've got, but we probably need to control how many workers we've got on those nodes, because using all 128 workers for quite a small matrix or quite a small array or vector is not going to give you good performance. So, unless you're going up to very large data set size, you probably want to be tuning exactly how many workers you're choosing per node, and taking it from there. But in very similar ways to what we could do with Dask or Python, we have these options for doing parallelization on ARCHER2, and as long as we follow the setup processes, we should be able to get good performance out of these, as long as we're not doing lots of small amounts of work and trying to do them in parallel. And then once you have something that's working, then the scope to go in and optimize and see, can we move this to a lapply instead of a parallel 4 or something like that, and what's the performance difference? As I said, that lecture doesn't take as long as the hour slot that's been given, so we've got plenty of time now for questions and then for practicals. But does anybody have any questions off the bat? So how do we optimize the Python environment available to users in ARCHER2 in practice? For optimizing Dask, is the burden optimization on the user? So the underlying Python optimization is really just making sure that things like NumPy, SciPy, and anything that's using in its configuration numerical libraries is built using the Cray ones specifically. So I don't know if you'll have seen it, but for Python, there is an Intel optimized version of Python which they release, and that does the same thing. It builds and installs NumPy and SciPy with MKL, the maths library. Here, what Cray are doing is building NumPy and SciPy with Python using their Cray libsci, and that just means that the numerically expensive mechanisms for doing high performance Python should be calling the optimized libraries on the system. That's what they're doing. When it goes to Dask, when you're installing distributed, what you want to do is make sure that you can target the high performance network if possible, but then beyond that, the optimization approach, is down to the user. So there's no real optimization of Dask itself by Cray. There's probably scope for doing some more work on that, but it's not their focus at the moment. Any other questions? If not, then there is also a set of practicals on the R side. So as I say, you can still play around with the Dask ones if that's what you're doing at the moment. Feel free to keep asking questions. There's also a set of practicals on the R side to look at similar kind of things. How do we run different mechanisms of doing R in parallel on the system? Give you some practical experience in doing that. So there's a folder called R with all the data sets in it, and then you'll see, let me share this again. You'll see there's a practical 5 is R, first playing around with that implicit parallelism we were talking about, where you can run R and it will use all the resources that are being used. It'll try and use all the workers here. You can see it's trying to use 108 cores at once. Then we can see that we can change the number of OpenMP num threads, and that will control how many workers it actually tries to use. Then that can be very useful. Of course, not all R is parallelized, so generally it's matrix multiplications that are parallelism. Things like creating matrices and stuff like that are not generally parallelized. We can also play around with data.table, which does some parallelization and stuff. But remember, if you're installing things on R, you need to export this R libs user environment variables first to make sure it installs it on the work file system, so you have access to that from the compute nodes. Then there is you can play around with how that works with the data table stuff and how that gives you better or worse performance by using different workers. And then we can start looking at the lapply, lapply, and follow through some of those examples there, going all the way up to doing parallelism with that snow library and those kind of functionality there. So we start off with a socket library and then go into the actually MPI version there, and that can take you all the way up to using multiple nodes at once. So feel free to have a play around with it. Thanks all for coming along. I understand if you need to leave and you don't have time to do all the practicals just now, perfectly fine. You have access to this account for another for 4 weeks, for a month, so you can keep coming back to them and playing them. And as I said, if you need to ask questions or if something occurs to you later, then you can go and just email me and ask me. That's perfectly acceptable. And then all I would say is I think I have one final. Let me have a look. One final lecture, which is a single slide, which is really just stop sharing this, start sharing this. Which is just to say, round it all off, ARCHER2 is a very big system. There's lots of resources there, which are things that can accelerate data science and data scientists' work. Loads of stuff you can do on it. It's primarily designed for large-scale parallel applications, but it can be exploited by large numbers of smaller applications and using the high-performance file system. So if you have 1 billion files to process and do work on, and you can't do that elsewhere, then ARCHER2 can be used for those kind of things. Or if you have large data sets to process, it definitely can be used for those kind of things. The software, generally you can get whatever software you want up and running on the system, either just by normally installing it or it's already there, or you can use this container approach to get more custom software on the system. There are ways that you can then optimize how you use the system by taking into account the placement of jobs, the placement of files in the file system, and exactly how you map things to the hardware. But beyond that, a lot of it should really run just as it would back on your laptop, but hopefully faster. So if there's any, you've got any interest or requirements, then do get in touch with us and have a chat. There's plenty of people around on ARCHER2 who can help people with stuff. Thanks for coming along to the course. As I say, we'll be around for the next hour or so. So any questions, if you want to keep going on the exercises, please do. And then there is the feedback, which is from a link here, but you'll get an email about, and it's very useful if you can provide it as well. So I know I've gone on and on about it now, but it's there for use. So any questions on the way, let me know. And otherwise we'll be here if you do have them.